Hello and welcome to this video. I'm going to talk about the Knuth Morris and Pratt algorithm for string and pattern matching. So what this algorithm basically does is it takes a pattern and matches it to a string. So say for instance, it's called the KMP algorithm, named after its founders Knuth Morris and Pratt. So say for instance I have a text or a string A1 till AN and I have a pattern B1 till Bm where m is less than n, then this algorithm is supposed to find whether the pattern exists within the text. Now, a very naive and brute force algorithm would be to start from A1 and check whether the pattern exists within A1 to AN, and then if it doesn't exist, then go on to the next character, do the same until you go to AN, and where you may or may not find the pattern. Based on that, you can output your observations. Now, while this algorithm works perfectly fine for smaller sets of strings and patterns, if you have a huge text and a pattern with a lot of repeated characters, a naive algorithm might not be the best algorithm to go with. But anyways, we will go with the naive algorithm first and see why it's not the best idea to use the naive algorithm for a problem of this kind. Now, the reason I put on this video is because I couldn't find a good enough video on YouTube which explains the concepts of the Knuth Morris and Pratt algorithm. There are several videos which shows the working, which shows how you can create the dynamic table. But the concept behind this algorithm, it's a pretty involved concept. Most of the videos doesn't explain that, and which I believe is pretty important, because unless you really understand the concept, there is no point in just rote learning the algorithm, memorizing the algorithm. Anyways, sorry for digressing. So we'll get back to the algorithm. So the naive algorithm would be pretty simple. So if you have A1, A2, A3 till AN, and you have B1 till say my BM ends here in under A3. So in that case, all I need to do is check B1 with A1, B2 with A2, and BM, where if we in this example take m equals to 3, whether this matches or not. If not, we move B1 to A2, B2 to A3, and BM to A4, and do the same thing all over again, which is absolutely fine if B1 is not equal to B2 is not equal to BM. But say there's a scenario where one or more of the characters do equal or do match in your pattern. In that case, is it a good idea to do this? Because if we are matching the same thing over and over again, we are doing repeated problems, and we can avoid that, as we have seen time and again in dynamic programming. So how do we go ahead and do that? So let's take two new strings and try and figure out a solution. So say we have a string, we have a text, like we discussed, A1, A2 till AN, and we have a pattern B1, B2 till BM. So what we have to find here is there a pattern that exists within A1 to AN that equals B1 to BM? Say we do find such a pattern. Say we take AI plus 1 till AI plus m minus 1, or sorry, in our case n minus 1, and we say this pattern or the series of characters till this point is equal to our pattern, which is pi till bm. No, I made a mistake. I'm so sorry. This should not be n. This should be m. Why? Because the size of the subset of the original text which matches the pattern will be the size of the set of the pattern. So if this is a subset, the cardinality of this subset will equal to, if this is a set, the cardinality of this set. So that's how it came. I mean, minus 1 comes because comes if we take a zero-based index. If it's not a zero-based index, then we just say ai plus m. So that's the basic concept. But how do we implement it as an algorithm? So let's observe. Let's make a very important but simple observation. We discussed earlier that if there were common characters in the pattern, so if there are common characters, we're basically trying to match the same character over and over again with the text, which we really don't need to do, because if there is a match for this of a certain character, say if there is a match for x, then of course there will be a match for x if the another x exists. So we try to avoid repeated work by somehow modifying the pattern, where both the modified version of the pattern and the original pattern are equivalent, yet the modified version of the pattern allows us to do, or I would say lets us to do, lesser work than if we were to use the original pattern. So say for instance, we take our pattern and represent it in this way, and I'm going to tell you why I would represent it in that way in a bit. So we say our pattern starts from b1, ends at bj, and there is one element in between called bk. So what's the use of doing this? Well, primarily we have to check whether we can take the pattern and see whether an initial subset of the pattern matches a terminal subset of the pattern. Say for instance, we find such a pattern that this initial subset matches with this terminal subset. If we can somehow find that property, then we know we don't actually need the entire pattern to be matched, because if I am matching the initial subset, then that is more than enough for me to deduce whether there is a match in the string. But which initial subset or which subset to take as the initial subset so that we can deduce a terminal subset or an equivalent terminal subset. Of course, if we were to find an entire match in the shortest possible time, we should take the maximum initial subset. How do we find the maximum initial subset? We take the help of regression, of course. We start from a bigger problem set or bigger problem space, and then we trickle down to smaller problem spaces as we see fit. So this is our problem statement now. In a problem space of b1 to j, we need to find the longest initial substring which is equal to the terminal substring for any j less than or equal to m, right? Let's denote this, we set our notations. Let's denote this by f of j. So what's f of j? We say f of j is b1 to k or bi to k if there is a proper substring which is both initial and terminal where k is less than j, or it might be so that there is no initial and terminal substring. I mean, there is no match, so in that case it will be 0. I mean, that's a possibility as well. So from here you can guess that it's not like we can throw away the brute force algorithm. If there is no match, if there is a 0 match, then in that case it's as good as using a brute force algorithm. So we might as well use a brute force algorithm in that case. But if there is a match, even a very small match, that will reduce our problem space quite a bit, and we'll see why in the subsequent part of the video. So now to mathematically define fj, that's the notation we took for representing the observation that we need to find the longest initial subset, which is also a terminal subset, and where j is less than m, less than or equal to. So fj equals to k. Say k is a point where we found till which we found matching an initial substring, which is also a terminal substring. If bi to bk is the largest proper substring of bi to bj, so b1 to bj, which is both initial and terminal. Suppose if we do not find one, then it's a 0. So how does that work? How does that work in a computer? Well, we defined our problem space something like this, right? And we said that, okay, here is my bk where it's supposed to match, but there's no guarantee that it will match at a point called bk. So we use divide and conquer. Okay, it doesn't match at a point bk, we can always go smaller. We can always divide the problem space into a smaller bit and try to find a k between b1 and bk and make that point our new bk. If we cannot do that, we divide further and we try to find another bk till a point where we cannot divide anymore, at which point we'll say we haven't found such a pattern and it's 0. So to write the pseudocode for this, we say for j equals to 1 to m minus 1, I equals to f of j, right? Now we need to find out that whether there is a mismatch. So it's a degenerating property. So we don't start looking out whether there is a match. We start looking out whether there is a mismatch. If there is a match, it is inversely proportional to a mismatch. So if we find a mismatch, then we know we figure out a mismatch till a certain point, and then we know that whatever the rest of it is there, that has to be a match. So it depends on a measure of dissimilarity rather than a measure of similarity. So we say while bj plus 1 not equal to bi plus 1, and I greater than 0. Of course, we are going from a bigger problem space to a smaller problem space, so the terminating condition will be that I will ultimately become 0, at which point we'll say that we have reached the end of the array and we don't need to proceed any further anyway. So say I equals to f of I. Now after we have completed that loop, we say if I is 0, then j plus 1 equals to 0. So when I is 0 means that we have reached the end of the loop and we haven't yet figured out a point or a pattern or a subset of the pattern which can measure to, which can form the initial substring and which is also equal to the terminal substring. So at that point we say that there is a terminal substring and j plus 1 might as well be 0, which is that we start from the beginning, the starting point. Else we deduce that we have reached a point in the array beyond which we have found a substring, beyond which the degenerating property that we used no longer work. So excuse me. So in that case, we know that the rest of the substring of the pattern till j is an initial string equal to the terminal string. So we say f j plus 1 equals to I plus 1, and that's pretty much it. So we got two loops, which gives us a complexity of n square. Now we have found the initial and the final substring. Now what to do next? Now we need to use this initial and final substring to create or to use it in such a way so that we can use this preprocessed part of the algorithm to compute for any and every string that might come in. So how do we do that? Right. So let's take the help of automaton, a finite state automaton now. Say we have a finite state automata or an automaton which has say states from 0, 1 till n, and if it's at state j now and it needs to jump to j plus 1, what does it need? So we define a finite state automaton with states 0, 1, say. Now somewhere here it has state j as well. So it needs to jump from state j to j plus 1. So what does it need? To understand this, let's take our string, our original string. So we have the original string, say a1 till as plus 1, and we found a matching pattern somewhere from b1 to bj, where as plus 1 equals to bj plus 1. So we found the initial substring and we found the terminal substring. If that is the case, then we can say that since, hey, we have found the initial substring till bj, now we know that as plus 1 equals to bj plus 1, which is the start of the terminating string or terminal string. So we fulfilled the parameters, fulfilled the arguments we passed before So this is a good time to jump from state j to state j plus 1. So if we represent this automaton using delta, so we say delta, we jump from j to say, okay, j plus 1 is probably misusing the notation, because we know it may be j plus 1, it may not be j plus 1, it may be j plus m. So we say, hey, let's take it as p. So we say we need to jump from j to p, which is j plus 1 if p equals to bj plus 1. Or what happens if we cannot jump from that state to the next state? In that case, we need to find such an automaton so that it fulfills a jump, or it uh, fulfills is probably not a very good word to use here, but it empirically allows us to jump from the fjth position to the pth position. So we need to just recursively find another automaton which allows us to jump from fj to the pth position for cases other than the first one. Having said that, how do we make that work in code? So let's call this our transition function. So how do we transit from one state to the other? So time to write some pseudocode. So what is our problem space here? How do we define a domain? How do we define a problem space here? So let's say we pick our notation as D. Not the best notation to pick, but I mean, it's really late and I'm kind of sleepy, so I'll just go with D. So we say P equals to B1 to Bm, and then we have got the rest of the stuff going on. So let's just take it as sigma. What's our base case here? So if we say D0 to B1, which is the first element, that's just one jump, we know that. If we say D0 to P for all P belongs to P1, well, it's just one element. P is not even in the set, so we cannot jump there. That will be a 0, of course. And then we can see the rest of the cases. I'll write out the pseudocode first, and then we're going to go through the pseudocode. We say for j equals to 1 to m, for each p belongs to sigma, g j p equals to j plus 1 if p equals to bj plus 1, else d j p equals to d if j p. What did we do here? Well, we said that we need to go from 1 to m, we don't need to check the entire pattern. Why is that? Because we found initial pattern and we found an equivalent terminating pattern, and so we don't need to actually check the entire pattern. We are pretty sure about that now. So what's our transition function here? So it just covered the initial pattern. That's as the same as covering the terminal pattern. So we say for start from 1 and go to the end of the initial pattern, and then for each one of those values we need to find a point in the P subset, which is P1 to Pm and then sigma. So P belongs to sigma, which is the rest of the pattern. So we need to find a point. So if we do this graphically, which is probably a better way to understand this, we have P1 to Pm and then a Bm to Name your notation. I don't know. K? No, we already used K. Not a good idea. K prime. Yeah, not creative. Anyways, so till this point we have the initial string or the initial pattern. But beyond that, we are saying that the entire thing is P, which belongs to sigma. Now P is a subset of sigma. P is a subset of sigma because P may not contain the entire space of sigma. So P could be a small part of sigma which matches the initial pattern, and that is quite possible. So that could be two cases like we discussed earlier. One could be that it's right next to Bm. Got it. I mean, that's the best that could happen. Or it could be in some other part of P, and that's what the else case does. It goes in recursively to find that point in the rest of the space. So again, two loops, n square, but this is the pre-processing step, so we're good. We don't really care. I mean, it's just one-time operation for whatever number of times you want to check a string for an available pattern. So you're good. Now comes the main part. I won't say the main part. Now comes the part where you check whether a pattern exists in a string. Now remember that this algorithm is mostly used for sequencing DNA, checking for patterns in DNA sequences. DNA sequences are really huge strings. I mean, and they have got like 4 proteins. I don't even remember. I gave up biology years ago, but like 4 proteins, and that's the sequences are a repetition of those proteins. So a pattern will have repetitions, and the pattern will usually be much smaller. So if n was your original string, then the length of the original string, m will be much smaller than n. So here we take n square, and you misuse the notation to write n square, but what we should actually write is m mod of sigma. Now there might be a case where sigma is really huge. In that case, running this recursion would actually take a lot of time, and which is ideally should not be the case, because like we discussed in DNA sequencing and all the stuff, the patterns consist of 4 proteins, so nobody really cares. But if there were a case where it did matter, we will talk about a small trick which could potentially help to write a better solution. Okay, I digressed again, and I apologize. So coming back to the main problem, how do we go through a string to match the pattern? So say we have a string a to a1, and this goes into an automaton. This goes into a finite state automata. So whenever the string goes in there, we take the pattern, and then we just match it based on okay, how do we put this? Okay, we take, suppose D, we talked about the D is a domain or D is a space, and then we say whether J prime should be included in the output, or whether to know whether J prime is a match, we say J and P. So what we're trying to do is we take the pattern, match it against the string, and we say, okay, J prime, the point J prime could be a match if it lies within the domain of J and P, right? So we match the initial, and we say if it matches the initial domain space, if it matches the final domain space, then we are at a point where we could say that this entire thing is a match. Now, compared to the brute force algorithm, where we went character by character and we tried to match every character to each other, this is a better improvement in the sense that we don't really need to match character by character. We know that if a pattern does not match in a character, that pattern is the longest sequence that we have that could match starting from that point, to the end of um, the modified pattern, or M in this case. So there is no need to check the next character against the entire character. I'm sorry, there is no need to check each character in the pattern. So you could say, hey, this does not match, so I just move my window along, because I know there is no point in checking the entire pattern, because I know that the pattern has already been processed, and if this longest sequence does not match, there is no way there can be a match in any of the characters that follows. So since we are shifting the window from character to character and actually not matching every character in our pattern, we can pretty much get away with this algorithm, get away with the runtime, get away with n runtime or linear runtime. So that is the optimization that KMP does. Now, as we talked earlier about a small trick which could come in handy if your sigma is really huge in those cases. So say if your pattern does not contain a few characters, is it possible that there could be a match of those characters in your original string? Of course not, because if the pattern doesn't contain it, you're not going to match against it. But there could be any number of such characters in your original string, and you know for sure that if a character does not exist in your pattern, there is no way that character could exist in your original string. I mean, there is no way it could match with your original string. So a character like A and D, if they're not in your pattern, that means nothing, even if it is present in your original string. So what you can do is you can eliminate those characters and replace it with one character. How that would help is, then you don't need, you can just, if you say I replace A and D with pound, in that case I do not need to go through pound, because I know that pound is not in my pattern and I can just completely ignore that portion. So how would you replace that? There are several ways. The brute force or naive approach would be to use a n-square algorithm, where you check against your original string, check against your pattern. If you find a character which is missing, go and delete it or replace it with pound. The better way to do it would be to create a BST with your pattern, do a login search over it, and look and search over it over when you encounter each character in the original string, and that would result in an n log n algorithm. So that's a trick that you can employ if your sigma space is if your problem space divided by sigma is really huge. Otherwise, that's pretty much what KMP does. I did not go into the source code of it because, I mean, it's pretty simple, as you can see from the pseudocode. Also, there are several articles and videos on YouTube that is the same thing, so you can refer to those. But this is the concept that drives the KMP algorithm. Thank you for watching the video, and I hope that this was of some help. Now if I can find out how to, there we go. Thank you.